Hello, everyone. Welcome to Hadoop Summit. Very good morning. It's a pleasure to open the operations track with a talk on Hadoop or Hadoops. Right? I really like the title Kishore came up with. We had lots of oops moment with Hadoop, and we'll share some of those things with you. So one of the things I really think that you will get out of this talk is we are using Hadoop at Rocket Fuel for the last 5 years. And we have grown from 3-node cluster to thousands of nodes today. And that's a unique perspective that we want to bring in today and share with you. We're not like one of those big companies who started out with thousands of nodes, but we started with 3 nodes and eventually grew to thousands of nodes. And we'll share some of the learnings and things that we have seen throughout this talk. First, just a few slides on who we are and what we do. So as you know, that web is still monetized by advertising. We are in business of digital advertising. So you can see the ads up here, or video ads, or ads on your mobile, right? They help monetize the web. Specifically, Rocket Fuel deals with a few delivery mechanisms of ads. The display ads that you see, the banner ads on top of web pages, or it can be a video ad, a pre-roll in your YouTube video that you see, all the ads that you see on your mobile, or the social ads that you see on your Facebook feed or on Twitter. Okay? So we deal with those kind of delivery. What we don't deal with is search and few other delivery mechanism. So I'm going to keep this fairly technical. Let me give you an overview of very core at Rocket Fuel, how it works. And hopefully that will set up a stage for rest of the talk. So that's a very high-level view of Rocket Fuel platform. We have a data storage, a machine learning models that provide the insights into which ad we should be serving. So it starts with advertisers like American Airlines, Target, Mercedes, BMWs, people who want to show their ad on internet. Working with us and giving those ads and the budget to us, right? Then it starts with the users like you and me, right, who are browsing the internet. As they browse the internet, it sends a page request to a sites, like you are browsing YouTube, or you are browsing Pandora, or some other site. On that page request, the YouTube and weather.com and those sites, publishers, they're going to send that request to exchanges. Exchanges basically act as an auction house to serve all these ads. Right? So there are a few examples: DoubleClick from Google, RMX from Yahoo, and things like that. So these exchanges are then going to conduct an auction in real time for the ad that is supposed to be shown to the user. Right? So that auction comes as a bid request to Rocket Fuel. We do our number crunching, use our machine learning algorithms to come up with the optimal bid and ad to show to the user. Right? And that ad will be served back to the user if we win that auction. Right? And we'll, of course, record all the engagement with the user subsequently. Right? So that's the core auction loop that Rocket Fuel really does well. In addition, we do get data segments from a third party that contributes to our decision making. So let's take a look at, zoom in a little bit and see what happens on that each request inside our machine learning engine. Right? So whenever we receive a request, we receive several bits of information on that request. So for example, which user is this? What brand affinity that user might have based on past data, what time of the day, what is the weather at that point in time at that location, which site that request is coming from, and so on and so forth. Right? Then we run our internal auction to figure out what is the best ad and what is the price that we are willing to pay for that particular serving. Right? And then we serve that ad back. Right? So that's what happened on each of those loops. And if you see a little bit deeper into what is going on in that internal auction is we evaluate each and every ad that we have in our database and come up with ranks and the values for various features, millions of features for each ad. and then pick the best ad that is for that particular auction, right? So that's what goes on onto this loop, right? And as you can imagine, this whole thing is less than 200 milliseconds. Right? I also want to put in the scale here. So the loop that you see here, that happens 45 billion times a day. So we receive 45 billion auction requests every day that we process and do all these calculations and evaluation on each of those requests. Also, latency is very important. As I mentioned that the whole loop is around 200 milliseconds. That also includes the network latency. So some of our systems, for example, the system that we use for user data lookup has a few milliseconds to work on, right? So this is just to put in perspective. So Blackbird is our HBase-based lookup system, which has only, it works in 2 milliseconds to retrieve the user data. And just to put that in perspective of a blink of eye is 400 milliseconds, right? So that's a quick introduction of what we do, what scale we are operating at, what are the latencies that we are dealing with. And I'll hand it over to Kishore to talk more about our architecture, scale, growth, and various operational things that we faced and our learnings. Kishore.
Thank you, Abhijit. Thank you, Abhijit. So I think you guys have now a decent idea about what our business is and how we do, right? So now let's look at the architecture that we use to support the scale of business that we do. Data centers, obviously. So as Abhijit mentioned, most of our transactions that we do in billions are latency sensitive. That means you need to have a worldwide presence to actually support all those billions of latency sensitive applications. And we have 8 data centers across the world, a few in United States, few in Europe, and few in Asia. Let's look at how we design our data centers, right? Not just ads, we optimize our data centers as well. So all these servers that you're seeing right here are designed based on our needs. They're custom designed, they're assembled and racked right here in our California facility. And then we test them, do all kind of testing, and then ship them to our data centers. So ship them to all the data centers, that means to international data centers too. So if you look at these 2 racks, this is the Hadoop rack that we have. The Hadoop servers are quite big. We have 12 by 3 terabyte disks, so they're disk heavy, so 20 servers will fill up 1 rack. Whereas our front-end servers, the bidders, they're small on disk but very big on cores. They're 40 that fill up half of the rack, but we actually run out of the port. So that's just 5% of rocket fuel. So what is 100%? We have close to 3,000 servers, and we have 188 terabytes of memory. That's everything in our infrastructure. That's almost 13 times bigger than the IBM Watson mission. Right? We have 42 petabytes of storage capacity, which is 106 times the whole data volume of Library of Congress. And look at what is Hadoop. That's the numbers that you just saw is whole infrastructure. So what is Hadoop infrastructure? So we have 1,400 servers today that run our Hadoop. And this 1,400 servers, they're running Hadoop just for analytics platform, but we have 300 plus servers that's used for our front-end HBase and Hadoop. So there's 1,400 servers that run our Hadoop as pure MapReduce, Hive, and data processing. They have 15,000 disks. You have huge problems when you have too many disks. You have to deal with disk failures. There are 15,000 cores, and there's 90 terabytes of memory that's used for all defining your JVMs or JVM for MapReduce slots and everything. And there's 30,000 MapReduce slots that are available to process all the MapReduce workload. And most important thing is we have 12,000 jobs that run every day on our cluster. And these 12,000 jobs that run every day on our cluster are not on 1,400 servers. It's just on our one primary active cluster. It's huge, right? So how fast we grown? And within 1 year, we grown by 8x. That means we had 200 servers a year ago, and now we run Hadoop on 1,400 servers. It's almost from 5 petabytes to 41 petabytes. So you have a lot of problems when you've grown very fast within a year, that to 8x, right? And we'll talk about how we maintain what are the typical problems that we have seen with the scale. But let's look at the architecture that we have today. This is not just Hadoop, this entire data architecture that we have. So the transactions start front-end servers, right? So whatever transactions, the latency sensitive that our ad servers or bidders, they log each and every element that our models can benefit from. So they log as much as they can here, and then we ship those logs to our Kafka cluster. And you have different consumers that read the logs from Kafka. So there's one Storm cluster that consumes the logs from Kafka for real-time processing, and there's this Kafka consumer this is HDFS consumer that pulls the logs from Kafka and puts in HDFS, and that HDFS data is in petabytes. Just remember one thing, right? So a friend of mine told me that big data is not just about volume; it's about how much of value that you make from data. And we try to monetize all the data that's there in the Hadoop cluster, and that's the scale in petabytes. We do data crunching and data processing on all the data that we got it in Hadoop cluster, and we use it for machine learning, reporting, ad hoc user queries, and everything. And then the most important thing, right? So you learn so much from your data by doing all kind of processing, and what are you doing with that learning? So we feed that learnings back to our front-end online HBase clusters, so that all the front-end servers knows about the real-time or the latest information about the users. This is more on how we have one of our primary active Hadoop cluster. This is a brief diagram. So we have HA enabled for name node. That's active on standby name nodes. Because of HA, they talk to general manager quorum. And you have zookeeper failure controls running on each and every name node. And they talk to zookeeper quorum. That's 5 servers. And you have a bunch of slave nodes. So we're trying to cover the hardware specs that we designed or we optimized for our workload. For all the master servers, we have 2x6, 6x2 terabyte disk, and we have 196 GB of RAM. We have 2x6 cores, that 12 cores, and we have 2 1 gig network interface cards on the master, just for the redundancy. But for the data nodes, we go heavy on disk. It's 12 disks with 3 terabyte each. And then there's 2x6 core with 12 cores with hyper-threading, it's 24. And you have 64 GB of RAM for MapReduce and other workloads. And there's 1 10 gig network interface because you need more network bandwidth to do all the kind of data transfer. So we talked about the business that we do, and we talked about the architecture that supports business. But now let's talk about the operation that actually supports the architecture. So because when you run on that scale of architecture, you need to have right principles to operate and maintain those clusters, right? First thing comes into mind for anything is maintenance. Especially with the big, large-scale Hadoop clusters, you obviously think, oh my God, how can I maintain this monster, right? So automation is the key, and you need to get started as early as possible. And fortunately, for us, at least we started from the day one with the Puppet, and it really helped us to scale a lot when we have grown in the 8x rate. And this other name that you're seeing on the screen, it's Infradb. That's all in-house written tool. It's very similar to what Puppet Hyra is doing today, but we have those needs 5 years ago. So we wrote it. It's just key value lookup service, and Infradb has everything about our infrastructure. So Puppet and Infradb are very tightly integrated and helps to maintain our clusters. So automate as much as you can. Don't try to do any manual instructions because your maintenance will become much. So today, if you look at some of the numbers, right? So if you have everything ready with the OS and everything, it just takes not more than 2 minutes for us to add an Hadoop node to the cluster, which means you're installing all the packages, you're creating the config files, and the config files with the right properties according to that node, and you're adding to the whatever Hadoop cluster that you intended to. So this is all done within 120 seconds today in just one node. And if you really want to bring up Hadoop cluster today, it doesn't take more than 10 minutes because that's how we've written all the manifest. And once you define that we need a new cluster in the one config file, then it just builds one cluster within 10 minutes. This is just one example that I want to tell today, right? So basically, automation is like what you define once, and you don't want to deal with it later. So this formula basically is very well written. So this is basically you take consideration of all the hardware resources that you have in server. So basically, whenever you scale or whenever you expand your cluster, right, you always try to keep it homogeneous. But it's really hard because whenever you want to expand, you always want better and bigger hardware. So homogeneous is not a point here. So with the automation, you don't have to worry about that. So if you look at this formula, it looks at how much of memory is there on the server, how many disks, how many cores, and then come up with a formula of number of MapReduce slots that machine can have. So whenever you go with a newer hardware and newer specs, you don't worry about defining the MapReduce slots again and again, because the Puppet and Infradb takes care of it. And this other thing where we use it for defining MapReduce, right? Your bigger cluster, you know that I want 2 gig for map and reduce tailed ops, whereas for the smaller clusters, I just need 1 gig. So you define once in one config file, and the config files are automatically generated on each and every cluster. So we talked about maintenance. So we know maintenance is we are adding nodes, everything is good. But if you don't tune your cluster, you're not getting performance out of it. True, the small clusters are easy because Hadoop community does a decent job. All the default values that comes with the configuration files just work. You see the value, now you want to expand, and that's when the problem starts. And that's what we have seen when we started growing very fast. And there are hundreds of properties in Hadoop, right? There's HDFS properties, MapReduce, and you have something else on JVM side, and the other ecosystem projects. Oh my God, how can you look at each and every property and tune it? And this one slide that I couldn't fit everything, so there's few that we want to share. You can definitely take a look at these properties and tune them according to your workload. So I'm not throwing out any values because it varies whatever depending on workload. So if you see in this slide, I want to share this bug that we saw that it solved a major performance improvement for job tracker, where job tracker was locking threads for some of the get counter calls. And those calls were very, very expensive. And we have seen improvement, like some of the RPC responses of job tracker was taking minutes. And after this patch, it came down to seconds. So I strongly advise, take a look at this patch and see if it helps your job tracker performance. Take a real issue, right? So first time when we had this out of memory issue, because job tracker does almost all the major work on the MapReduce side, it runs out of memory. So first time when we had it, why it happened. Search in Google, you found out all the threads. Now we see that this is a bug, and there's a bug that opened in community, and everybody says, yes, there's a memory leak. And 5351 got fixed, but then unfortunately, it created one more bug that's called 5508. And then that got fixed in later version. So do you have to keep upgrading cluster or upgrading your patches? So they gave a workaround saying that, hey, put this property, and then it doesn't load all the files. We're not actually doing the file system get call. But it didn't help. So now we started, stop searching Google and start working, right? So that's when we take all the dumps and find out this interesting thing. If you see this object, the 1,000 instances here, but the memory it's taking is only 500 MB. So, but the major chunk of 8 gig is by counters. You don't know what counters are those. So this is interesting, right? Job in progress is for each and every job. So when you go to job tracker UI, you see running jobs, completed jobs, you'll see retired jobs. Whatever number of jobs that you're seeing on the UI, those are supposed to be coming from memory. And everything else are from disk. So if you count all those number of jobs, you should see exactly same number of instances here. But no, at that point when I took this screenshot, I had 300 jobs running, completed, and retired, but I'm seeing 1,000 instances in the heap, which means the number is not matching. And why is it happening? So we did a lot of testing, and then we finally found out this undeclared formula pattern that we found. This property called how many completed jobs that you want to keep per user. So that is actually dependent on per user. So if your company grows, and if you have large scale, and if more number of users started using, that means more number of jobs are in the memory. So we had 100 plus users. That means every job by default, the property value is 10. So 100 in 10, there you go. You have always 1,000 jobs in the instance right there. So we started tuning these properties, right? We don't want 10 jobs per user. Reduce it. And retire your jobs as fast as you can. So once the jobs are completed, it stays there for some time before it gets retired. So retire them as soon as you can so that they can get clean from your memory. And then by default, this property is 1,000 jobs. Do you really want to keep 1,000 jobs in the memory? And those 1,000 are retired jobs. It doesn't really make sense. So you can always go to job history and then pull them from the disk. So reduce it to the low level that you can. And after all this, we never seen out of memory in the job tracker. Touch wood, right? So we talked about maintenance performance. And how do you know that your cluster is really working? You built it and everything. So if you don't really monitor it, if you don't have visibility, you don't know what your cluster is doing. So monitoring is very important, that's key. This is exactly what we have, in front of operations area. So we have a huge displays right there. If something goes bad in the any node or in the cluster, it shows up right there. So and management is sitting next to you. Hey, something is red. You have to look at it. So there is no escape. So that's good, right? Put it in front of operations area and have your people look at it all the time. Some more graphs that I want to share. Right? There's tons of metrics similar to tons of properties in Hadoop. You really have to know what properties you want to look, or what properties you want to tune, what metrics you want to look. There's few interesting things that probably don't really know that it is important. This is called call queue length. It's mostly on how many RPC queue calls are in the queue. That means if your HDFS is so slow, if it's taking too long to process any RPC call, you'll see big spike in this. So if you see this, it went from order of 10 to magnitude of thousands. So it stayed there for few hours in 3,000. So let's say if your RPC call queue length went from 10 to 3,000 for few hours, that means your HDFS is dead slow during that time. And you really don't know if you don't really monitor these metrics, because by the time you go look at something, it will just automatically get fixed, and it will always stay there if you don't really look at all these graphs. So visibility is a key. And there are different metrics to monitor, like JVM heap size and the HDFS IO. And apart from HDFS and MapReduce, right, you should always monitor the infrastructure. Well, the network, you have load, you have CPU percentages and everything. So you can monitor this. And we use Ganglia, we use OpenTSDB. So Ganglia, by default, Hadoop pushes everything to Ganglia. So that's good, you have everything there, but you really need to know what to look at, right? OpenTSDB, we have custom collectors that send the metrics to it. And this is more on workload. So you're monitoring daemons, you're monitoring everything, but what if your actual workload is not working fine, right? You need to really understand how many jobs are getting launched, how many kill jobs, how many failed jobs are there. And then how is your map and reduce slots getting utilized? How many are waiting? And how many are being utilized? That's same for map and reduce. So if you really know, if there are too many of waiting and if it's not getting utilized, there's some problem that you can better optimize and have this extra percentage get used instead of having the wait time. So that increases your map reduce jobs performance. So we talked about HDFS and map reduce, but Hadoop is not just map reduce and HDFS, right? If you want your better performance from Hadoop, you really have to understand the other infrastructure components like network, servers, and everything. And network is always complex. People always complain about network because it's one of the area where you have very less visibility. So stop complaining. So this is one dashboard that we have. And it's basically, all the 8 data centers are connected via mesh. It's all mesh network. And this mesh can be really mess. If something goes wrong, you really don't know what is it impacting and what are the problems. So this shows, this is all the packet loss that we are having from data center to data center and via which provider. And this is more on latency. So if you have latencies and if you have packet losses, in a real time, you'll see on this dashboard and somebody is getting paged. So good. We are monitoring, people looking at metrics and everything, but monitoring is not just enough because you cannot have people stare at the screens whole day. You need a better alerting so you can sleep well and get notified whenever needed. Right? What are the different types of alerts that you can have? Obviously, check whether name node and job tracker are up, otherwise you're fired. If your name node goes down and you don't have an alert, you have to answer your management, right? So that's a no-brainer. And the other optimization we do, right? So you have hundreds of data nodes, hundreds of task tracker. If you start getting alert for each and every daemon being down, that's a noise. So you have to cut down noise, so use summary and aggregate alerts where you define a threshold. I want to know if my 10% of task trackers are down instead of 1 being down. There's this custom JMX metrics that available for name node, job tracker, everything. You can go to this URL, and there are some beans that you can look at. We monitor dead nodes, number of missing blocks, number of corrected blocks, and everything. And pretty important, we realized this in hardware that this is important metric too. The FS state, which means it tells about whether a cluster is operational or not. HDFS can just get into safe mode for no reason. Just tons of reasons to get into safe mode, saying that I'm running low on resources, I'm giving up. And if your HDFS is in safe mode, that means you cannot write anymore. All your applications start complaining. And you really need to know when your name node is not operational. So do have an alert on this. And this is same for workload. So we have an in-house return tool which uses Hado. It's a Ruby gem. Talks to job tracker on Thrift client. It pulls all the information and complains about long-running jobs or even jobs with high memory and reduced tasks. And this is important. So we collect all the details. Whenever there's a task tracker, blacklisted task trackers, you don't get any alerts because the task trackers are still up and running. They're fine, but they're not taking any workload. That's a problem. You're losing your capacity, right? So we collect all the details, like what are the task trackers that are blacklisted, why it got blacklisted, what are the jobs that were running on the time when they got blacklisted, and then automatically restart them. So they will join back the cluster, and your capacity is almost same. You're not running on the reduced capacity. And then we go later, look at the details and see how we can avoid this blacklisted task trackers and what is causing it. So you can also always pass the log file of job tracker. You don't have to really worry about the libraries or version within Hadoop 1 and Hadoop 2. It's just a log format. You can change the regex and get all the information. We use this. We collect all the information like job ID, the user who is submitting, which queue they're submitting, what time the job started, what time it ended, everything, and we put it in a MySQL database into a nicely structured schema. So everybody can just query from MySQL with all the data. And it's right there in MySQL. So everybody knows MySQL, so they can run SQL queries. There's an UI that runs on top of MySQL. And most important, White Elephant, H7, yes, they can help. The scheduler metrics, they're very important, and there are two ways to get the scheduler metrics. You can go to this HTML web page, which is there by default, or if you enable metrics servlet, you can get the metrics in /metrics. So all this is now being given by multi-tenancy, right? You have data in HDFS, you have tons of data, and everybody in the company wants to use that data. Can I run my jobs, or can I use that data? You cannot say no. So that's a problem with multi-tenancy. If you really don't define the resources that everybody can use, you'll run into lots of problems. And we have lots of components. We use it that uses Hadoop cluster. And for a good multi-tenant cluster, right, you need to really have a good scheduler. Otherwise, you'll run into all kinds of SLA problems, one job impacting others. And no scheduler is perfect. You really have to understand, I'm not getting into discussion of phase share versus capacity, because that's again another discussion. But any scheduler that you pick, if you don't measure it and if you don't understand it, you're not doing it right. So this is what we do, right? We get all the reduced tasks in the map task demand, see which queue is demanding more, and which queue is getting what phase share, and how many running tasks are there in queue. So you can now compare who is demanding more and who is getting what. And now you can really talk to those teams and see, do you really need this? Or you're demanding more in the mornings and not in the nights, so can you stagger your jobs? So these are some things that you can really do to really use your workload or capacity that you have in Hadoop cluster all day long instead of trying to use everything in the morning. So these metrics are really helpful, and you should take a look at it. That's about operation side of it. And I'll talk a little bit about BCP and YAN. BCP, what is BCP? The business side of definition, it's a business continuity plan. You can also tell us disaster recovery, right? So we have a disaster recovery cluster sitting right there, equivalent to primary cluster. All the data that we need from active is getting replicated to BCP cluster. And now BCP cluster, we use it for primary use cases like reporting. We run real-time reporting because we have data, why not just use the resources? We run real-time reporting, and we try to run all the models, refreshing all the model that pipelines are run on BCP cluster today. So before BCP, this is what our architecture was. All these front-end servers, they write all the logs that they can, and then we ship all the logs directly to Hadoop cluster. And then we run data scrub, do data processing on it, and use that data for user queries, reporting, and modeling. And we do keep some backup in Amazon. Now with the BCP cluster, there's some logs that are directly going to LSV data center, and there is processed information that we ship from primary to active instead of sending all the raw logs to both data centers, because that's your network complication, and also you don't want duplication of data. So we ship it to primary, process it, and only send limited and much needed information to the BCP. And we have a dedicated point-to-point network connection with 10 gig bandwidth, and it uses for just the replication, and this replication is taken care by our own Hive tool that we developed in-house for our needs. And this data now, don't wait, don't have your BCP cluster just sit idle. You have tons of capacity, use it, right? So we use it for ad hoc queries, for research, for modeling, and everything. Talk about Yarn, because that's where we started Yarn with. And yes, Yarn is in production. It became production ready a few months back, but yeah, we're running at scale. There's 700 nodes that the size of cluster where the Yarn is running. The primary use cases, right? No more job tracker. You have all kinds of problems with job tracker because that guy was doing everything that it can. So now no more job tracker. Workload is handled by all the daemons equally. There's resource manager, node manager, and the application master. The other interesting thing that for us was hierarchical queues. So in the scheduler now with the multi-tenancy and everything, you have 5 different queues, each queue for each application or each team. Now the team comes in and say, hey, we have different SLAs for every person in the team. Can we run our jobs? It can possible, right? 1 queue for team. But now with this hierarchical queues, you can have child queues inside a parent queue, which means more multi-tenancy and more problems. But yeah, it's a nice feature. So that's you're getting in Hadoop too. What are we using at RAN and Rocket Fuel? As I said, it's in production. We are running at a scale. There's, I think, 31 terabytes of RAM. No more predefined slots in Yarn. So you don't have to define how many map reduce slots for a server, and you don't have to define how many of them are map and how many of them are reduced. So even though you have open and not used to reduce slots, you cannot use it for map, even though there is a demand. So now they're just map and reduce. So you're not defining them anymore. You're defining them as part of containers. Your jobs ask for specific requirements, like I need 1 gig of RAM, 2 cores, and Yarn will just give it to that job. So no more static slots, and we are map reduce and Hive heavy. So that's a primary use case today. And we are looking into tests, Spark and Storm. We're testing it for a long time. They're all in the race, so we might push them to production anytime soon. So, because once you have Yarn, it's not just map reduce. Map reduce is just one of the applications. So you can run tons of applications. You can write your own. And these are the good applications, and that works for our use cases. So we are looking into this. I think that's pretty much it, what we want to cover today. Yes, we're hiring. We have a booth. Come visit us at the booth, and we have another presentation, I think, tomorrow at 4:35, if it doesn't get delayed again. 4:35, we talk about our core technology right there, so you can come visit us and listen to our another tech talk. Thank you. We have 7 minutes. We can take questions.
What version of Hadoop are you running?
So with the Yarn, we are running Apache 2.4, which is the latest in community right there. Yeah.
Do you consider to use cloud solution?
Well, can you repeat it?
Consider cloud solution.
Consider cloud solution. We were in cloud, but with the scale that we were growing, the cost optimization, everything is better, and we were trying to design our own hardware. So we have limited options in cloud because they're predefined instances and everything. So we want to mostly optimize the hardware and use accordingly for our workload. So we moved away from cloud and started in-house our own data centers.
Yeah. Just to add, I think 5 years back when we started out, we prototyped it on Amazon Cloud. But as we grew, it was obvious that we want to have our own hardware, control it well, and it's definitely cost effective actually. Question back there. Yeah.
Okay. The question is, do you guys use any virtualization? No, it's all bare metal servers. We're not using any virtualization for Hadoop. We do have virtualization, but not for Hadoop. No, we haven't tried any virtualization.
No, we haven't tried. I think there was not enough motivation when you own the hardware and you can optimize that to bare metal. That's a question.
Restore data from cloud?
Sorry.
Restore data from cloud. Said backup.
Oh, yeah. So on that slide, I think what we do is there are certain subset of our data which is really, really critical for business. We back up that in Glacier.
When do you restore?
When do restore? We haven't restored that. And with the BCP cluster, now we have 2 copies of that data sitting there. So it's, that's why we push everything to Glacier now, not even to S3. It's like really that disaster case, right? You have lost both the data centers. You can still operate.
There's one question.
After switching to Yarn.
Unfortunately, I don't have specific numbers because we started just 2 months ago using Yarn. And even if I give you some numbers, right, our primary cluster, as I said, there are 12,000 jobs that run, they fight for resources, but Yarn is not that heavy yet. So there are free resources always, so you'll immediately get resources, so your jobs are much faster, obviously, on it. But I think with just Yarn, right, with getting rid of job tracker or even predefined slots, you'll definitely see more 2x improvement right there.
Just to add, actually, don't want to quote the numbers until we do apple-to-apple comparison. As Kishore mentioned, right, the cluster with Yarn is not that much loaded right now, so it looks much better. But I think we have in our plan to do apple-to-apple comparison just to understand this better. But there should be obvious benefits. I just may want to get to the numbers.
Have you, or are you planning to do anything with devs?
Yes.
Yes. So I think we use Hive pretty heavily. I think there was one slide in data architecture which mentioned, but Hive is very popular in Rocket Fuel. Everybody, including salespeople, use Hive. We are testing Taze, and we have seen good performance. Again, we don't have the apple-to-apple numbers, but we are considering moving to Taze here on Yarn.
So you have 6 or 7 data centers, and you are presumably running bidders on most of the data centers, and they're all pushing logs to your main Hadoop cluster, correct? So like while pushing so much logs, like how do you manage the both the latency and the cost, like the network cost of pushing so much data to your Hadoop?
Right. So I think the question is, we are pushing data from all the 8 data centers to our data center where all data is processed. How we are managing the scale and the network cost. So I think we developed a in-house tool long back, which uses DistCP to copy data from all the serving node to the main Hadoop cluster. So each of those nodes act as a single node Hadoop cluster, sending data to the main Hadoop cluster. So it's essentially hundreds of nodes sending data to hundreds of nodes. So it scales really well. So we never had an issue where logs are backing off and things like that. In terms of cost, I mean, that's the value proposition, right? If we get all that data and we process it and bring models, it is going to bring the value. So
like, do you use like Amazon backend for pushing data, or do you use like dedicated fiber networks, or do you use just like a public network? Like, do you do anything special for connecting this data center to your Hadoop cluster?
so question is, do we use any cloud infrastructure to send this data, or we just use dedicated? So we have dedicated lines between our data centers. As Kishore showed on one of the slides, that we monitor that network, the mesh of around 8 data centers, and we use that infrastructure to send data around.
Next question.
Are these slides shareable? I think so. I think we'll figure out. I think the presentation will also be available online. I think so.
Tell us more about your disk-based environment. You have an online space and an offline space. Do you tune them differently? And so,
So-
what's your reason offline?
Yeah, can you go to that slide? So question is, can you talk more about your edge-based use case? You see online and offline edge-based. So yes, we use edge-based quite heavily for both use cases where we look up information from edge-based in real time, and that's what we refer to online, and all traditional MapReduce use cases in our primary Hadoop cluster. And yes, we do treat those 2 clusters very differently. The online cluster is optimized to give a performance of 2 milliseconds, whereas offline cluster is more traditional cluster with big block sizes used for traditional MapReduce workload. So are there different properties? So we gave a talk on in edge-based conference on our online, so you can refer to that with lots of detail how we actually tune to get that kind of performance out of online edge-based. Okay, one last question. So question is how we upgraded 2 points.
So we started with Yarn on the new cluster. We started with 2, and then we upgraded from to 2.2, and then when 2.4 released, we upgraded from 2.2 to 2.4, but not actually from 1 to 2. From 2 to 2.4, yes, it was smooth. Those minor issues, but we tested it properly in our staging environments.
Cool. All right. Thanks, guys.
Cool.
We run out of time. Thank
Thank
you very much.